For 20 years now, we've been mapping the structure of complex networks, and I believe it's fair to say that we now have a pretty good grip on their main structural characteristics. Therefore, the question that remains is how do we translate everything we know about network structure into predictions about their actual dynamic behavior? I like to think of the network as a static roadmap. And here's the challenge, that we all know that the same road network can exhibit profoundly different traffic patterns at 8 a.m. in the morning or at 2 p.m. in the afternoon. This is of course just a metaphor, but it illustrates to us that identical networks can give rise to highly distinctive dynamic behaviors. To treat dynamics, we need to add another layer of description. First, we have the network structure. Then on top of that, we have the interaction mechanism. When we draw a link between node I and node J, what does that actually mean? Does node I consume node J? Does it infect it with an epidemic? Or does it chemically bind to it? We can capture these different mechanisms by adding a nonlinear component to our system. The gray term captures the network topology, and the nonlinear orange terms, they describe the interaction mechanisms driving the system's dynamics. So now that we have a modeling framework, the question we need to ask ourselves is what exactly we wish to predict. Or in other words, what do networks actually do? I would argue that whether we focus on how viruses spread in a social network, how failures propagate in an infrastructure system, or how biochemical signals penetrate the genetic network, it's all about how information spreads through the system. At some point, one of the nodes has an activity perturbation, it sparks, and this instigates a signal that then travels through the network to impact all other nodes in the system. Now I know what you're thinking. That should be simple. First you impact the nearest neighbors, then the next neighbors, and so on. But the challenge is that when we combine complex networks with nonlinear dynamic mechanisms, we get a much richer picture of propagation patterns. Sometimes it really does work like that, spreading from the source outside through the network layers. But here, for example, it seems to spread from the periphery to the center. A very counterintuitive form of propagation that indicates the difficulty in mapping structure into dynamics. Even the propagation timescales range over 6 orders of magnitude despite being run on the exact same networks. This diversity in propagation patterns all boils down to a single number. You see, we can predict that a node's intrinsic response time, tau I, scales like that node's weighted degree Si to the power theta. Yeah, but why should you be interested in that? Well, if you're a physicist, you should be excited because this exposes a universal scaling relationship. What seemed diverse and unpredictable actually follows a unifying principle, a hidden universality behind the zoo of propagation patterns. But mainly, if you're a network scientist, this scaling provides us precisely with what we were aiming for. Si, a node's weighted degree, represents a structural element, part of the well-mapped static topology of the network. Tau I, on the other hand, a node's response time, is a dynamic function that we would very much like to predict. And theta? Theta is an analytically predictable dynamic determinant that helps us link between the two. It translates structure, Si, into dynamic predictions, here a node's response time, tau I. Let's see how this comes to life. Going back to our metaphor, think about the network as your static roadmap, and the signals, the information, are like cars traveling between the nodes. Now, if you're in the theta positive regime, then the hubs are bottlenecks. They're the slow responders, and so the hub-enriched pathways become the signal propagation traffic jams. But then, on the exact same network, if we change the dynamics and enter the theta negative regime, the same network components fundamentally change their behavior, as now the hubs are the freeway and the peripheral nodes, they become the traffic jams. Basically, theta provides us with a network GPS. It predicts a delay at each junction and can help calculate the exact signal travel time between all destinations. We can use this to lay out the nodes, and we find that the zoo from before follows predictable and tractable propagation patterns. This, to our knowledge, is the only existing dynamic layout. Just like a GPS predicts different travel times and different routes at different times of the day, our layout locates all nodes differently depending on the nonlinear mechanisms driving the system's dynamics. So the diversity of propagation patterns all boils down to the single dynamic parameter theta, which helps us systematically translate structure into dynamics.